Hi and welcome back to our video series about determinants. In today's video, we're finally going to have a look at some examples. Remember, we've summed up the most important rules for doing matrix computations before. So now I'm going to show you an example for those rules. Specifically, we're going to look at an example for Cerus Rule. We're going to look at one example for doing Gaussian elimination or route operations to obtain triangular form. And also we're going to have a look at Laplacian expansion. Let's start with the easiest case here. And that's probably Cerus Rule. Now remember, Cerus Rule can only be applied for 3x3 matrices. Not 2x2, not 1x1, not 4x4, and nothing larger as well, just 3x3. So we need a 3x3 matrix to use that. And let's say that is 1, 2, 1, 3, 7, 4, 4, 10, 9. You might remember that we've seen this matrix here already. So we know the determinant, and we can check whether the result is actually correct. So how does Cerus Rule work once again? We just copy the first two columns, so that's 1, 2, 1, 3, 7, 4. And then we have a look at the diagonals. So here's the main diagonal, and we also need the two diagonals above that one. That's why we copied these columns. Remember, those will count with a plus sign. So those will count positively. Whereas these diagonals here will all be counted with a minus sign. So what do we get? Let's start with the positive ones. So along this diagonal here, we have 1, 7, and 9. So it's 1 times 7 times 9. Then along this one, we get 3, 10, and 1. So 3 times 10 times 1 plus. And finally here we have 4, 2, and 4. So this is the positive parts. Then for the negative parts, we have 1, 7, and 4. So this is minus 1 times 7 times 4. Here's 4, 10, and 1. So minus 4 times 10 times 1. And last but not least, 9, 2, and 3. So minus 9 times 2 times 3. So what is the result here? 7 times 9, that is 63, plus 3 times 10 times 1 is 30, plus 4 times 2 is 8 times 4 is 32. And for the negative parts, 7 times 4 is 28, so minus 28, 4 times 10 is 40, and 9 times 2 times 3, it's 9 times 6, that is minus 54. So what we get here is, let's see, 60 and 93, that's 125 for the positive parts. Minus and the negative parts sum up to 122. So the remainder here is 3. And if you remember that we've computed this matrix already using a different method, using the definition to be precise, you might recall the result that we got then was also 3. So hopefully both of these computations were correct. So that's Cerus Rule. Once again, only for 3x3 matrices. I cannot stress this often enough. Let's move on to the next method. Part B. Next, I'm going to show you using elementary row operations to obtain a triangular matrix. So I said already that this method is particularly useful for matrices that are larger. So I'll use a 4x4 matrix to demonstrate that. Let's say we're using this specific matrix here. And to make it a little more interesting, I'm even going to include a parameter here. So that last entry here, that's an alpha. Alpha is an arbitrary parameter in the reals. And I want to know how this determinant depends on alpha, so I'll have to use a method to compute it depending on that number. Now what I'm going to do is I'm going to apply elementary row operations to obtain echelon form. So first I'm going to select a pivot in the first row. This is going to be my pivot, and I'm going to make row operations to obtain zeros here below that pivot. And I'm going to do that by subtracting the first row from the second, subtracting 2 times the first row from the third, and subtracting 3 times the first row from the fourth. Now what I do in these operations is I'm adding a multiple of one row to some other, or I'm subtracting a multiple of one row to some other, the same thing. That does not change the determinant, remember. So what I'm doing here is not changing the determinant in any way, so I can just write this is the same thing as the determinant of the new matrix. And the new matrix, well, I get that by copying the first row. Then for the second row, I have 1 minus 1 is 0. 0 minus 2 is minus 2. 1 minus 1 is 0. And 1 minus 0 is 1. For the third row, I'm subtracting 2 times this first row here. So what I get here is 2 minus 2. 0 minus 4. 0 minus 2. And 1 minus 0. And finally, for the fourth row, sorry, this one here, I subtract 3 times this row. So I'm subtracting 3 from the first entry, that yields 0. I'm subtracting 6 from that second entry, so I get a minus 6 here. I'm subtracting 3 from this entry here, so that's a minus 2. And then 0 from that alpha entry here, so that's an alpha again. And I can see I obtained 0, 0 already. Next step, next step after this pivot, I'm now going to choose this entry here as a pivot. Remember, if that was not a good choice, I have also the option of exchanging rows, but in this case, that's an excellent choice. So I'm going to just go with that. And I want to obtain zeros here below that pivot. So I'm going to subtract 2 times that second row here and 3 times that second row here. And again, these operations do not change the determinant, so I can just write an equal sign here. I'll copy the first and the second row because those will not change. Now for the third row, that 0 is of course still a 0. And I get minus 4 minus 2 times minus 2, so that's minus 4 plus 4, that's 0. Minus 2 minus 0, it doesn't change. And here I have 1 minus 2 because of that factor here, so that becomes a minus 1. And then for the last row, I get 0 here. -6 plus 6, that's a 0, of course. Again, the -2 does not change. And here I'll have alpha minus 3 times 1, so that's alpha minus 3. And you can see I'm almost done. So here I have echelon form already. Next pivot I'm going to choose is this one here. And I'm just going to subtract that third row from the last one. And again, that's an operation that does not change the determinant. So I can just copy the first 3 rows here. Those will not change in this operation. And for the last row, I get 0, 0. And I have -2 plus 2, that's again a 0. And then I have alpha minus 3 plus 1. So that yields an alpha minus 2 here. And what I have now is echelon form. So you can clearly see I can now use the entries on that diagonal because I clearly have a 0 block down here. So we have triangular form. And that means the determinant is simply the product of those entries on the diagonal. And that's 1 times -2 times -2 times alpha minus 2. So what we get here is 4 times alpha minus 2. And that completes the determinant. So you can see for larger matrices, that might be some work that's involved here, but that's natural for larger matrices. You can't get around that work very well. But these operations are a good way of computing the determinant. It's a systematic way. It's a way you should have practiced very well in other contexts. So hopefully you'll make less mistakes trying that approach. So for larger matrices, I would advise that you at least consider that approach before you embark on anything else. And now finally, I'll show you some other approach, and that's Laplacian expansion. And again, we are going to use a 4x4 matrix. We're going to use one that is very similar to the one we've just seen. I'm just going to replace the alpha by a constant that we know. So this is going to be the matrix that we'll deal with. And if you have some experience in Laplacian expansion, then of course you'll immediately spot that this is ideally suited for Laplacian expansion. Because have a look at that second column here. What you can see here is there's 1 non-zero entry and 3 zeros. And you will remember that each summand of that Laplacian expansion also contains 1 entry in that respective column or row. So in this case, we'll have 3 entries that contain a 0 times something. And of course, those will all be 0. So no need to compute them. The only remaining one is the one corresponding to this 2 entry here. So that's what we're going to do. We're going to use Laplacian expansion with respect to the second column. Well, what do we get? Let's see. First thing we have is, of course, the sign. We'll have to have a look at the sign. That is -1 to the power of row plus column. So we'll start with this entry here. That's in row 1, column 2. So that's 1 plus 2. And remember, that's row plus column of the current entry. This current entry itself is the number 2. And then we need to multiply this by the determinant of a cofactor, and we get that cofactor by deleting the column and the row corresponding to that current entry. So we're left with this column, and this column. So let's copy these. That is 1, 2, 3, 1, 0, 1, 1, 1, 1. And again, all the other entries that would come from this entry and this entry and this entry, all the other summons are going to be 0. I'll just write those at the end, something like following is 0 plus 0 plus 0. So no need to actually compute anything here. Okay, so that's the first step. Now we're down from 4x4 to 3x3 matrices. So for the 3x3 matrix, let's again apply Laplacian expansion. Again, let's have a look at the rows and columns and see if we can find any zeros. There's just 1 0 here, so we might either use that column or that row. And just for the sake of having a row as well, I'll use this row here for my Laplacian expansion now. Okay, now what happens here is we'll do an expansion with respect to second row. Let's first copy all of these. So here we have -1 to the power of 3, that's a -1. And here we have 2, so that's a -2. And then we'll compute the determinant here. I'll copy that once again to make things a little easier for you. So that's 1, 1, 1, 2, 0, 1, 3, 1, 1. Again, we'll do expansion with respect to this second row here. So what do we get? For the first entry of that row, we have this 2 here. So the first part of the expansion is -1 to the power of. This is in row 2, column 1. So we get 2 plus 1 times 2 times, and the determinant that we need stems from the cofactor we get by deleting the second row and the first column. So we're left with this row and this row. So that is simply the determinant of 1, 1, 1, 1. Plus, now for the second part, here's a 0, so we just have a +0 there. And for that last part here, we have a non-zero again. We need to take care of that. Yields, again, a sign that is -1 to the power of row plus column for that entry. That is in the second row and the third column. So we have a 2 plus 3 here. Times the entry itself, that's a 1. Times the determinant that we get by deleting that second row and the third column. So we're left with this row and this row. Right, so that's 1, 1 and 3, 1. And finally, we're down to 2 by 2 matrices. So that should make it easy to compute that result. Again, we copy that -2 here. Here we have a -1 times 2. So again, a -2 times, and we'll just use the 2 by 2 formula now, 1 minus 1. That's easy. That's nice. And then for the green part, -1 to the 5th, so that's again a -1 times 1. So -1 times, and the determinant here is 1 minus 3. So what do we have? Well, we have -2. That orange part is 0. That green part here, 1 minus 3 is -2 times -1, so that's a +2. So what we get in the end is -4. And that's the final result for this determinant. And that's also the final example of this video. I'll see you in the upcoming videos.